First one will be by my graduate student at Caltech, Viraj Karambelkar. Viraj, if you want to share your screen, and you'll be telling us about a ground-based pathfinder infrared survey.
Yes. Are my slides visible and am I audible?
Yes.
Okay, I've also pinned the timer. Okay, good. Okay, thanks, Mansi. I'm going to talk about the potential of near-infrared searches in searching for these very elusive kilonovae that were very nicely outlined in the previous talk. And to do that, I'm going to describe a new exciting near-infrared surveyor that we are building specifically for this purpose, called Winter, and then describe the potential that Roman has in actually being the discovery engine and doing electromagnetic follow-up of gravitational wave triggers to find these kilonovae. So as was mentioned in the last talk, kilonovae are fast fading transients that are expected to accompany binary neutron star mergers and some neutron star black hole mergers. And kilonova emission is typically expected to have two components. The one is this blue component that is powered by a very fast moving polar ejecta material. And the other is a more isotropic, the other is a red component that is powered by more isotropic material that is rich in lanthanides, and that is this material is released in the merger process. So it's not clear whether the blue component is expected in all kilonovae, because the presence or absence of the blue component depends on several parameters of the binary, such as the inclination of the binary, or the lanthanide fraction in the ejecta, the mass ratio of the binary, or the lifetime of the remnant that is formed after the merger. But the red component is thought to be pretty much ubiquitous in kilonovae, and as a result, kilonovae are generally expected to very quickly shift their emission into the infrared and be much brighter in the infrared wavelengths than in the optical wavelengths. Despite that, almost all previous searches for gravitational wave counterparts in the electromagnetic spectrum have been conducted in the optical wavelengths. So this plot shows the landscape of EMGW searches that were conducted during LIGO's previous observing run, O3. And on the x-axis is the wavelength of the search, on the y-axis is the depth that was achieved in the particular search. All these different surveys are plotted as different colors, and the size of every marker is proportional to the field of view of the telescope. And it's very clear that there is a distinct lack of near-infrared searches that are as sensitive as their optical counterparts. However, during O4, we plan to change this because winter is coming. And winter is, so what's winter? Winter is a new near-infrared time domain survey that will operate from a 1 meter telescope on Mount Palomar. So in this figure, you can see the winter telescope in its tiny little dome, and in the background is the famous 200-inch telescope on Mount Palomar. Winter will have a wide field of view compared to other near-infrared instruments. Field of view is about 1 square degree. It will operate in the near-infrared Y, J, and shortened H filters. And the unique thing about Winter is that it's making use of this new Indian gallium arsenide sense detector technology. And if you want to know more about the technology and the innovations that went into building Winter, please check out this poster by Daniel Frostig, who is also attending the conference and has done a lot of hard work in actually building Winter. And she'll be very happy to answer any questions you may have about the technical sides of Winter. So Winter is expected to go on sky in spring 2022, and it will perform the most sensitive near-infrared time domain survey of the northern sky, achieving depths of about 21st magnitude AB in the J band. We are excited to do all kinds of science with Winter with this really new first of its kind instrument, but during next year is the year when LIGO 04 is expected to operate, and during that time, the main science goal of Winter is to do EMGW follow-up of gravitational wave triggers issued by LIGO. And we wanted to find out how would Winter perform, how would this near-infrared survey instrument perform during O4, given that its field of view is small compared to some other optical surveys that do the EMGW follow-up like ZTF or Atlas, which have few tens of square degrees of field of view. But given the fact that Winter has the unique advantage of actually looking in the near-infrared wavelengths. And so to check this, we put together a simulations paper with Winter. This paper is now published and is available at this link. And I want to mention that this paper was mainly put together by 4 graduate students, Daniel and me from the Winter team. And we collaborated with Sylvia and Geoffrey, who work with the LIGO group at MIT. So I'll quickly describe our end-to-end simulation in one slide. We started by simulating binary neutron star mergers in the universe based on existing rate estimates. Then we passed them through the relevant LIGO pipelines, identified which ones will be detected in gravitational waves by LIGO, generated these localization sky maps for them. Then coming to the electromagnetic side, we simulated the optimal tiling with winter using optimal scheduling algorithms. So you see the sky map in shades of red, and each black pointing that appears is winter pointing, and is a winter tiling of the sky map. And finally, we used different models of kilonova light curves to simulate what electromagnetic emission we expect from these. And putting all of this together, we estimated how many kilonovae can winter actually detect during O4. And so here are our results. For assuming realistic binary neutron star merger rates, we expect to detect anywhere between 1 to 3 kilonovae, to discover 1 to 3 kilonovae during O4. And although this exact number varies depending upon what light curve model you use, or what different parameters you use for the light curve model, such as the lanthanide fraction. And as Jennifer mentioned in her previous talk, the expected emission from kilonovae can be really sensitive to all of these assumptions. But this is very encouraging, because it shows that even with a field of view of 1 square degree, winter can efficiently tile the localizations that you expect to get during O4 and actually discover kilonovae. Second question that we wanted to explore is, what are the actual advantages of having a near-infrared search? Is there any parameter space where a near-infrared search performs better than an optical search? And we found that the biggest advantage was for kilonovae that were aligned, the binary neutron star mergers that were off axis. So these mergers were not aligned along the line of sight to them. And so in that case, the blue emission is expected to be very suppressed, because it's expected to be concentrated around the poles. And if you have an off-axis kilonova, and the kilonova has an inherently high lanthanide fraction, so that it's inherently red, then the advantage of near-infrared is even better. So this plot over here shows, given a particular set of kilonova ejecta masses, what is the maximum distance out to which you can detect the kilonova. In the R band and in the J band, if the limiting magnitude of both these searches are about 21 magnitude. So bluer in this plot means larger distances, and you can see that for these so-called red off-axis kilonovae, the J band can discover these kilonovae to much larger distances than the R band. And in fact, if you go to specifics for GW170817 like masses, you can detect in the R band, you can detect the GW170817 like kilonova if it was red and off-axis only to 170 megaparsec, but you can detect it in the J band to about 1.5 times larger the distance. And we found that in a simulation, we found about 25% of the LIGO detected binary neutron star mergers are these off-axis mergers. So in principle, if all of them could be red, but if a significant fraction of these are red, then the near-infrared observations will be very crucial to actually discover the kilonovae associated with them. A second advantage that we found is that no matter what the geometry of the kilonova is, it is just inherently longer lived in the near-infrared than in the optical. So these plots show the probability of detecting a kilonova as a function of luminosity distance and time since merger. And you can see that a darker shade of blue means a higher probability of detection. So the probability of detection quickly drops to 0 for in the optical within like 3 to 4 days, but it stays on. You can still detect kilonovae for more than 8 days in the near infrared. And these red crosses over here are actual events from a simulation. And you can see that in general, the detection probabilities are much larger for these events in the J band than in the R band. So all this discussion was about binary neutron star mergers, but if you look at neutron star black hole mergers, they are expected to be even redder. And that's because most models predict that the blue emission will be highly suppressed in neutron star black hole mergers. And this is what we confirmed using this model. So if you make a similar detection plot, you can see, but using neutron star black hole merger models, you can see that NSBH merger kilonovae are not only detectable for longer in the infrared, but they are also detectable for much larger distances in the infrared, irrespective of their inclination angles. And so these were the main takeaways that we got from the winter simulation. And we are very excited about actually going on sky during O4. Maybe during the next Roman conference, I'll be presenting actual results from O4 rather than this simulation. But in the remaining 3 minutes of the talk, I want to talk about the future of EMGW observations, especially from the near infrared point of view. So looking forward, what do we expect from the gravitational wave side? We expect that we expect to have much better gravitational wave detectors. There are many upgrades that are being planned for the existing 3 detectors like LIGO, Kagra. And we expect to have a completely new LIGO India detector joining the network in somewhere in the next 5 years or so. And so as a combination of all of these, having these sensitive detectors and having the more number of detectors and longer baselines, we expect to detect much further binary neutron stars and neutron star black hole mergers, and the localization areas are going to be much smaller than what they currently are. On the near infrared side, we are also building many new near infrared instruments. Winter will already go online during 04. And we also have many exciting upcoming projects like the DREAMS telescope at Siding Springs in Australia, the Cryoscope telescope at Palomar, and of course, the Roman telescope, the Roman Space Telescope in space. So this is what the landscape of EMGW observations might look like during in the next few years. And I want to focus on the mainly the near infrared end. So we'll have Winter and DREAMS at the J and H bands, the Cryoscope telescope at the K bands, and then what will be much more sensitive than all of these, which was alluded to also in the previous talk, will be the Roman Space Telescope, which really there'll not be anything that that matches the sensitivity of the Roman Space Telescope. Now, I would like to remind you that the sizes of the markers on this plot is actually proportional to the field of view. So maybe some people might be discouraged by seeing this very small field of view of Roman, but especially compared to something like LSST, which is plotted as black stars over here. But what is important is that in the Roman era, we will have 4 active gravitational wave detectors. So the localization areas are expected to be much smaller than what they are. And there are many simulation papers which predict that there will be tens, if not more, events that will be localized to areas better than a few square degrees during the Roman era. And those can be covered with the Roman field of view in very few pointings. And finally, the advantage of Roman is again evident if we make similar detection plots with say a search of 25th magnitude in the J band and compare it to a 25th magnitude search in the R band. We can see that in the J band, the Roman Space Telescope, we can discover kilonovae for much longer than in the R band. And so this advantage always stays. So I'm almost out of time, so I'll leave my summary slide on. And leave my summary slide on screen. And I'll just say that Roman just promises to be a very pioneering telescope in not just studying, but also discovering gravitational wave, binary neutron star and neutron star black hole mergers. And it's going to be a really exciting time. Thank you.
Thank you, Viraj. Questions for Viraj? I hope people will actively ask questions, especially to our early career presenters. And it should be probably evident to everybody that the SOC wanted to support early career researchers in this conference and give them opportunities to speak. So, questions? Silence. Okay. Skylar,
I have one. If I can speak, it's easier than just the typing.
Yeah, go ahead, please, Anya.
Nice presentation. I had a question about your plans with Winter with respect of like if you detect a kilonova candidate, are you planning to publicly communicate these through channels like TNS, etc., or this is something that you have discussed already?
Yes, we do plan on publicly releasing the compelling kilonova candidates through standard GCN circulars and the usual procedures that have been followed in LIGO 03, TNS, GCN, astronodes, all of those things.
Thank you.
Thank you, Anais. Any other questions? Yeah, feel free to unmute or just raise your hand if finding the right Slack channel and typing in it is clunky for you. Okay, if not, let's move on to our next talk.